From scattering theory, applications were born, full pun intended. Two such applications are reflection and transmission coefficients and the optical theorem, which we see put to use here. So for this video, we have a 2-for-1. In problem 18, we wish to use the one-dimensional Born approximation to compute the transmission coefficient, given that t is equal to 1 minus r, for the scattering from a delta function and from a finite square well. Compare your results with the exact answers. And then in 19, we wish to prove the optical theorem, which relates the total cross-section to the imaginary part of the forward scattering amplitude. So sigma equals 4 pi k in an imaginary part. Pretty darn cool. But why do we care? Well, this is all applications of scattering theory, and of course we like to make sure that our results are self-consistent. That'll be very important to us here soon. So the challenge for you is, where can we use the optical theorem? And I'll link one such usage of it here in the description for you, which was the cover image. Don't forget, although we have 2 questions today, most of it is in the video, but you can find the PDFs that will be posted on Patreon for you to keep in your collection. No big deal. If you want it, just comment and I'll send you the link. And of course, if you're curious about the world of science, be sure to subscribe. I post educational content every week to quench your thirst for curiosity. So with that, let's jump right in. Alright, so stop number 1, we run straight into problem 18. Let's first start with the delta potential, and what we see is that the reflection coefficient, which is given from 10.103, takes this form where we have some constants up front, m over h bar squared, k all squared. Pretty normal stuff that we've seen in this chapter. The infinite integral, now we have e to the 2ikx with the potential. And since the potential here is the delta potential, that was given to us by equation 2.117. Okay, thankfully with the delta potential, we know how to use it in integrals pretty quickly. So push this constant alpha out front, no big deal. Now we're left with the delta, but because it's a delta, this tells us that we have to evaluate the integrand at the point that the delta is centered on. So that would be 0 here. Thankfully, we know that e to the 2 or e to the 0 is 1, so the absolute value of negative alpha is just alpha. Square that, and then we see we are left with an alpha squared. No big deal so far. But let's square all the terms and our constants here, because we still have to bring into account the energy via the wave number k here. So when we square everything, tidy it up, we see that k here needs to be looked at a little further. And we see that k squared was defined as 2me over h bar squared. So when we do this, we get a factor of h bar squared canceling. That's the 2 right there. With that, the mass terms cancel, so we get all confined here. Pretty easy. So then we're left ultimately with the reflection coefficient of m alpha squared over 2h bar squared e. Putting that into the relationship with the transmission coefficient, which is just 1 minus r, then we see that we get this transmission coefficient, which isn't too bad. But how does this compare to the exact result that we found back in chapter 2? Let's find out. So here we have the exact result, again given by equation 2.144, and we see that we have something that looks a little weird here compared to what we had just proven, or rather just found, not proven. But we know that this is all to the negative 1 power, and putting it in this form, realizing that this kind of looks like the 1 over 1 plus x, we can use a binomial approximation on this exact answer. And in doing so, what we get is 1 minus m alpha squared 2h bar squared e, which is exactly what we're trying to get from the Born approximation side of this equation. But this is only true provided that this thing right here, this thing is much less than 1, which is stated here. Okay, so that's the only way that the binomial approximation works. And again, in the PDF, I sent some links to help you with this again. I don't remember it always right off the top of my head, so I don't expect anyone else to. But yeah, definitely use that. And then what we see here is that this puts an energy restriction on us, because if we push this E over, we see that E has to be much greater than all of these constants, or all of these constants have to be much less than E. Whatever way you want to work it, that's the condition we need. So under this assumption, they are good to go, and they are pretty good and equivalent. All right, so enough rambling. Moving on to the finite square rule then, the reflection coefficient, again from 101 or 103. We now have to be aware of the limits on the integral from the formula because the potential here that we want given by 2.148 is the finite square rule, which is only defined for having this potential in the interval -a to a. Okay, but after that, this is a pretty easy integral to evaluate. Just get the constant out front. Now we just have an exponential integral, not too big of a deal. We see that we just divide by 2ik. Now, a little bit of foresight here will tell us that if we take this k out and then just evaluate this exponential, something cool is going to happen. So let's just try that out and see what this simplifies to. So as promised, we take the k out here, leave the 2i in there. And then we have the limits evaluated up here. But if we notice here, this is an exponential minus a negative exponential, again, complex though, over 2i. This is the definition of the sign from the complex world. And so we get sine of 2ka, which is a pretty darn clever simplification in my opinion. And we were wondering, how would we get sine out of exponentials? Well, that's how. Go back to Euler's equations if you wish. That being said, when we square everything in the constants just like we did last time, we get m squared, h bar squared squared, and then k squared. But now when we take the magnitude of this thing squared, we get v naught and k squared as well. And then we have sine squared. But note that we have three parts where we have k's there. So if we substitute in the definitions, we're going to get a lot of cancellations as we're seeing here. 2me h bar squared squared. That gets rid of all our h bars here with this one and this one. Both the mass terms cancel with this one and this one. And so what we realize that we have left over is just 2e in the denominator and a v squared up top. And then down here, we just got to get rid of this fraction here and put 2a over h bar, clean up this root. That's what we see here, the next step. Note that I have a v naught squared, 2e, that's all squared, and the sine is squared. So I can take this and square a bracket on the outside, which makes our life easier when we're finding the transmission coefficient. And that's what we see here. 1 minus r brings us to this. Now, if we remember from chapter 2, this looks kind of familiar, but we still have to prove it. Let's see how we do that. So this is the exact answer, and we know that it takes the form from equation 2.172. And once again, we still have this form of 1 over 1 plus something. So if that's the case, we can use the binomial approximation again with the stipulation that this whole thing is less than 1. So then we have a negative here, and then we have now a linear term, get rid of the fraction. Now within this, we see that the only way that this can hold and make this such that it's less than 1 and all those other things that we need is that v naught has to be less than e. And as such, when we put this in, we see that this essentially goes to 0 in this scheme, which will leave that to 0, which is fine. We need this to be really small in order for the binomial approximation to work anyways. So this stipulation makes sense. But with that, we see that we're left with just e down here and e inside there. Now, when we clean it up, we get, a v naught squared. A 4 goes to 2 squared. This e, and this e go to e squared, sine squared again. We clean up the argument of the sign, and we see that once again, we get something that looks like just what we had shown. So indeed, these do yield the same results, and it's pretty fascinating how these self-checks, how these things kind of self-check themselves with the appropriate limitations. So self-consistency here is pretty awesome to see come through. That being said, if you're finding this helpful, don't forget to give it a thumbs up. It helps more curious minds like you discover this content. And with that, we conclude problem 18 and we can jump straight to 19, which will be very fast, so hold your foot. All right, so stop number 2 then, we get to the optical theorem, which is actually pretty cool. I didn't think we would see this here. I remember seeing it in E and M, but not in quantum, but I guess it makes sense. But first, what we need to do is to evaluate the scattering amplitude at theta equals 0. Scattering amplitude was given by equation 10.47. And here, all that means is that theta equals 0, so we plugged it into the Legendre polynomial, cosine of 0 equals 1. But when we talked about Legendre polynomial, we know we had to be normalized and all those other nice things. So we know that that equals 1. Upon doing so, it simplifies our expression of this, but we see that we are going to have to split this exponential up. Okay? Doing so, we see that we get a cosine plus I sine. No big deal. We've seen Euler's identity before. Pretty easy. But then what we can do is distribute this into both of these purple terms, and then we can start to segment it. And by segmenting, what we see is that also distributing this 1 over k into both of these terms, what we clearly observe from both of these color codes is that there is a real and an imaginary part of the scattering amplitude, and hence the need for magnitudes in the differential cross section. Okay? As such, these parts are defined as the real part of the f of 0 is equal to everything that we saw in blue. The imaginary part was everything that was in green. We're just real and imaginary, pretty much complex numbers, so nothing new there. But now, if we decompose the total cross section given by equation 10.48, what we see is that we have 2L plus 1 sine squared. So if we take this k squared and put one factor inside, which we do here, all of this looks exactly like this. So we can just plug this in, but with the leftover 4 pi k, and when we do that, we see that we have just proven the optical theorem. And that concludes question 19. I told you it wouldn't take long to prove this one, but I thought it was pretty clever, all things considered. All right. Well, that was a fun exploration of a couple applications of the scattering theory that weren't too, monotonous and tedious on the brain. But pretty cool to see how, again, old results coming through, even back from chapter 2 with the scattering and transmission reflection. That's kind of a natural appeal to it. The optical theorem, I think, is used a lot in laboratories with the sensors. Like I said, I showed one application early, which again, I'll link in the description because I think it's cool. But that being said, the stuff is getting a little dense, and the next chapter is not going to be any easier. So it would probably be wise of us to review all the old math tricks that we've seen before, especially those binomial approximations, which we've seen not only in this class, but also in the Griffiths E&M book, because there's just a lot to deal with in that approximation. Reciprocals are not fun to deal with. That being said, don't forget about using tools like the Shams, tables and integrals. Those are very helpful. And any other books and integrals that you have, those will definitely help you soon. So that being said, please, if you find value, share this with a friend who's also curious about science, and let's grow this learning community together. It's been a wonderful journey so far, and I can't thank the supporters of this channel enough. As you see, the support group is getting bigger, and I am eternally grateful for your support. It keeps me going even when I'm feeling lazy and don't want to. So thank you, thank you, thank you. That being said, books, notes, and other reference materials will be found below or in the PDFs. If you have any questions, please feel free to reach out. And as always, thank you for watching. Until next time, stay curious.